Good morning, sir. I'm Charita from the Department of ECE. I'm pursuing my BTech second year in Srinivasa Ramanujan Institute of Technology. My topic is about autocorrelation function, its definition and properties. So I'm going to give a brief introduction on the topic. In signal processing, we often need to understand how a signal behaves with time, whether it repeats, how random it is, or whether it is a hidden periodic pattern. One of the most important mathematical tools that helps us to do this it is the autocorrelation function. Autocorrelation gives us an idea how much a signal resembles a time shifted version of itself. In simple of terms, it measures the self similarity of a signal. If a signal looks almost the same when shifted in time, it means it has some repeating patterns. If it looks completely different, it means the signal is random. This makes autocorrelation extremely useful in areas like communication, radar systems, image processing, seismology, and speech analysis. Autocorrelation means it measures how similar a signal is to shifted version of itself. It helps in identifying repetition, periodicity, and randomness in signals. Widely used in communication systems, radar, audio processing, and pattern recognition, as I said before. Definition: the autocorrelation function, that is ACF, is mathematically defined as r to the xx of tau equals to limit intends to minus infinity to infinity x of t into x of t plus tau into dt. Here r xx of tau is the autocorrelation of the signal x of t, and tau is the time lag or shift between the two versions of the signal. The integral multiples the signal with its time shifted version and adds integrates the result overall time. For discrete time signals, the formula becomes Rxs of k equals to sigma n to infinity equals to minus infinity x of n or x of n plus k. Essentially, the autocorrelation tells us how much the signal at the time t and the same signal at time t plus tau are related. The autocorrelation function of a signal x of t is defined as I said before, or xx of tau equals to integral x of t into x of t plus tau into dt. For discrete time signals, or xs k equals to uh, summation x of n into x of n plus k. Tau or k equals to time lag indicates how much the signal matches with the shifted version of itself. It's a brief explanation that I have given before. Physical meaning: autocorrelation reveals self-similarity in a signal. A high value of or excess of tau means the signal strongly resemble its shifted version. A low or zero value means weak or no similarity. A tau equals to zero, correlation is maximum, signal compared with itself. The physical meaning of autocorrelation is quite initiative. When t equals to 0, the signal is compared with itself, so the correlation has its maximum value. This means the or excess of 0 represents the total energy for an energy signal or average power. As increases, the overlap between x of t and x of t plus tau changes. If the signal is periodic, the autocorrelation will also be periodic, repeating the same pattern. If the signal is random, the autocorrelation quickly decreases and tends to zero for large tau. In short, a high value of Rxs of t is strongly similarity between signal and its shifted version. A low or zero value, weak similarity that signal doesn't match itself for shift after shifting. Detailed explanation of properties. Mathematical representation, that is autocorrelation function, has several important mathematical properties, that is even function or excess of tau equals to or excess of minus tau. Maximum at zero lag or excess of 0 is the maximum value since the signal is identical to itself at zero shift. Energy and power relation. For an energy signal, or excess of 0 equals to E, that is integral x of t. For a power signal, or excess of 0 equals to P, that is average power of a signal. Non-negative deficiency. The autocorrelation function is always non-negative definite, meaning or excess of 0 greater than or equals to mod or excess of tau. Fourier transform relation and power spectral density and periodicity. Symmetry even function or excess of tau equals to or excess of minus tau, where symmetric about tau equals to 0. Maximum at 0 lag, it is the highest since the signal is compared with itself. Energy signal, power signal, non-negative nature, Fourier relation and periodicity. Applications: detecting the repeating patterns and signal periodicity, estimating power and energy of a signal, used in speech analysis, radar or sonar and communication systems, helps in noise filtering and future extraction. And also, I'm going to give another more applications like communication systems, speech and audio processing, radar and sonar systems, seismology, medical imaging, economics and data science, randomness testing. And also give I want to give advantages, that is reveals hidden periodicity or repeating patterns in signals. It provides a measure of signal energy and power, bridges the time and frequency domains through the Fourier relation, essential for filter design, spectral analysis and pattern detection. Graphical representation: it shows how r excess of tau varies with time lag tau, symmetric about tau equals to 0 and maximum at 0 lag. Periodic signals produce oscillating curves. Random signals show a sharp peak at tau equals to 0. Summary: autocorrelation measures self-similarity of signals. It helps identify periodicity, energy, and randomness. Properties: even, maximum at 0, non-negative, energy or power related, periodic. Essential in signal processing and communication applications. I conclude that, in summary, the autocorrelation function is one of the most powerful and analytic tools in signal processing. It helps determine how signals relate to themselves over time and is crucial for understanding periodicity, energy, and randomness. By studying the autocorrelation curve, we can easily distinguish between periodic, random, and noisy signals, which is essential in almost every modern engineering field. Whether it's used in communications, audio systems, radar, or data analysis, autocorrelation provides a deep insight into the inner structure of signals, helping us better systems and smarter decisions. Thank you.